So we're going to walk through another example of a t-interval, and we're going to do this without data. The question reads, an environmental scientist is measuring the concentration of a particular pollutant in a lake. They take 18 water samples and find that the mean concentration is 0.052 milligrams per liter. And there's a sample standard deviation of 0.008 milligrams per liter. Construct a 99% confidence interval for the population mean. We can see here that we're working with means. It might also say average, so just keep that in mind. But we're looking to find the population mean. So that means we would need to use a z-interval or a t-interval, and we can narrow this down to using a t-interval because this question does not give us the population standard deviation. The standard deviation that was given to us comes from the sample. It doesn't say it's from all the members in the population. So this has got to be a t-interval. We can also see here that we have a small sample size that also indicates that we have a t-interval. Okay, so the information that we need to put in on GeoGebra to get our confidence interval, we need our sample size, which we're told is 18. We need our confidence level, which is 0.99. We need our point estimate, which is the sample mean. That was 0.052. We need our sample standard deviation. We were told that that was 0.008. And we're also going to do this by hand and check to see if our answer by hand matches GeoGebra so that we can practice. So we will also need to find our t-critical. We need to make sure that we're on t-estimate because we're doing a t-interval for the mean. We're doing a 99% confidence interval, so I'm going to change this to 0.99. The mean was 0.052. The sample standard deviation was 0.008. And our sample size was 18. So you can see here that we have a lower limit for our confidence interval as 0.0465, and we have an upper limit of 0.0575, and our error is 0.0055. Let's find the t-critical so we can also use that to find our confidence interval by hand. We have our student t distribution that's on there. Our degrees of freedom is 1 less than the sample size. Our sample size is 18, so our degrees of freedom is going to be 17. Because we're doing a 99% confidence interval, there should be 99% in the middle for the shaded area, which means there's 1% total left over. And then when we split that between the two wings, we have 0.5% in each wing. So I'm going to check the left wing first, and I'm going to put in 0.5%, which as a decimal would be 0.005. So our critical value is on the left side, negative 2.8982. When we round it to two places, that's going to be negative 2.9. Now let's check the right wing. When I'm looking at the right shaded area, I want that to be 0.005. And as you can see, we get the same value, just the positive value, because we're on the right side of the distribution. So when we round that to two places, we get 2.9. So we can check it by using the between. I'm going to put in our T critical before it's rounded. We want to show that it's between negative 2.89823 and positive 2.89. Oops, I forgot my 823. And when we do that, you can see that the area between those two values is 0.99. So we know we have the correct T critical value. So I copied down our lower limit and our upper limit from GeoGebra, and I copied down the error that we got from GeoGebra, and I also copied down our T critical. So let's see if we get the same thing when we do this by hand. So our error is equal to T critical times the standard deviation divided by the square root of n. So I'm going to take 2.9 times 0.008, which is our standard deviation, and divide by the square root of 18. When you work that out, and when you round it to 4 places, you get 0.0055. So the error checks out. Now, when we add that error and subtract that error from our point estimate, we get our upper and our lower bounds. So to get our lower bound, we take our x bar, 0.052, and we subtract the error. When we do that, we get 0.047, which other than rounding differences is exactly what we got here. Now for our upper bound, I would add the error. When we do that, we get 0.057. Again, it's pretty close to what we got. It's just a matter of rounding. If we had kept all the digits and we didn't round that error, we would probably get the same answer as what GeoGebra got. But because I rounded this to 4 places, it probably threw it off a little bit. All right, now for our conclusion, we would say we are 99% confident that the true population mean is between 0.0465 milligrams per liter and 0.0575 milligrams per liter.